introduction, and thanks everybody for being here. Actually, can we turn the mic a little bit down? I think it's just at the brink of feedback, so just a little bit lower. And yeah, let me just start this. And as Hossein said, ask questions as we go through the talk. I actually planned out a lot of different things, but we don't have to get through everything. This is like a school. You should determine the pace of how we go through things, and you should give feedback. And if things get too quick for you, then the best way to slow me down is just to ask questions. On the other hand, if you tell me you know something already, then we just skip that part. There are many options. So what I want to talk about in these three lectures that I have here is basically start out with an introduction. So that's what I was feeling. With an introduction into ultra-small atoms, and basically coming from the point of view of experimental physicists, want to give you an introduction about the system, how we probe it, what kind of physics we can realize with it, and give you a few examples today. And then on Thursday and Friday, of course, going into depth of some more modern things also concerning kind of the non-equilibrium dynamics. And I think this will connect very well to the other speakers. So kind of today, the challenge will be to lay the groundwork for you to know what the systems are that we're working in and what our detection capabilities are. And I'll give a few examples of that, and we'll see if we make it down to the absolute negative temperatures. That should be a fun part if we make it there. So that's really a kind of interesting part because it touches on a lot of deep questions on thermodynamics, of how we define temperature, how it's connected to information entropy and questions like that. And also just by itself, you know, some puzzling things that are quite counter-cutting to what you typically have in your, what you probably learn in your lectures. Tomorrow I want to talk a lot about quantum magnetism, and that's probably going to connect a lot to Thierry's talk and Fabian's talk. A lot of stuff in 1D, dynamics, polaroids, again there's a lot of connections. And the third lecture I haven't decided yet. Probably I will talk about MBL, so that would connect a lot with Dima here, or on topological things, but we can decide that on Thursday what you would like to hear actually. Alright, so let me get started here and talk about the systems. And the systems we're studying, not only now are set up, is general quantum many-body systems, and you know that they are relevant for many different applications, but also just fundamental science, and basically trying to understand the underlying processes behind many of these materials with emergent properties that we're trying to unravel. And there's really nothing better than having a very controlled environment in which we can study that. And one of these environments that people are looking at today are these quantum simulation, quantum computing approaches, which are now, of course, all about, and you're hearing a lot about them. Probably if you were at the APS meeting, you were hearing a lot about these efforts, following a little bit the spirit of Richard Feynman's vision to use these highly controllable systems, quantum systems, to build quantum many-body systems with new control and observation techniques to do things we really can't do in standard solids. And I think you'll hear many examples in the talks about that. So I will talk about these systems of ultra-cold atoms trapped in, we call crystals of light. There are, of course, other systems, these ion traps or superconducting devices, for example, where people actually try to do similar things in different scenarios. So in general, we're going to talk about are systems like this. This we're going to go into much more depth. This is the so-called Fermi-Hubbard model, which is a very primitive model of discussing how electrons interact on a lattice, behave on a lattice. It has very simple terms. It just describes basically the electrons moving through the lattice through these destruction and creation operators. So you have a lattice and the electrons hop from one side to the next one through tunnel motion. So that's basically the kinetic energy part. And then there's a very simple interaction, which is this on-site interaction where, for example, a spin up and a spin down. Remember, we can't have the Pauli principle two spin ups on the same side if we're just considering lowest energy band physics, so we have to have a spin up and a spin down on the same side, then they can interact, and the strength of this interaction is just determined by this parameter u. Right? Now, we can calculate this in our atomic scenarios, but this is just also for real materials, just given by this parameter u. And then there can be some other terms which are typical for the AMO systems that you can have this harmonic trapping, for example, underlying these. Now, first thing to note here is that this is, of course, a dramatic abstraction if you're coming from a really complex material like these copper oxides that I've shown here, And if you're telling me you can describe them by something like that, that's of course, you know, a great abstraction and not at all clear whether the physics of this material is captured by this simple model, but we can of course ask whether essential features of this system are captured by this simple model. And that's why we're studying this and putting so much emphasis on this, because this really only has these two terms, kinetic energy and interactions, but you'll see throughout the talks that out of these very simple terms you get actually very complex many-body behavior. You get things that you cannot even know what the phase diagram, for example, of such a system in 2 dimensions is, although you would say from a Hamiltonian point of view this is actually really, really simple Hamiltonian. But it turns out it has actually a great deal of complexity, and we'll hear more about that. So for cold atoms, I think there are basically 3 challenges to which we like to contribute to the experiments. On the one hand, we'd like to provide new probes and analysis techniques to long-standing known problems, where we maybe know the solution already, but we can look at these in completely new ways and analyze them in new ways, and you'll see many examples of that. And then, of course, we'd like to also put out quantitative predictions. We'd like to really tell on these precisely known models, you know, what do our experiments give us as reference points. And for example, if we look at this celebrated DC-DCS crossover, we can measure the equation of state, and then we can compare the different models and really then, you know, test, you know, which of the models is correct and which one is false. And maybe the third, maybe the most exciting part, of course, if we can realize completely new phases of matter that have no analog in existing systems. This is kind of maybe the third line. And I don't want to say 1, 2, or 3 is better than each other, but I think we're contributing to all 3 of these, and that's basically the things we can do. All right, so how do we do that? Well, here's a real material. Okay, you see it? This is this tiny thing here, angstrom size, spacing, and typically in order to look into this material, you want to have a really good microscope. Okay, that's why people in solid-state physics, they build these XFEL, new X-ray sources, or SLAC, these new light sources, to look into such materials, because they're so tiny that they're even hard to see on the screen. So, but what we can do, take a drastically different approach, is basically try to build a material which is 10,000 times bigger than what we have in the real material. So if we could do that, then of course everything that becomes micrometer distances here, it's angstrom distances here, becomes micrometer distances here. And on top of that, everything that happens on very fast timescales, picosecond, attosecond timescales, will happen on maybe kilohertz timescales here. So all the dynamics will be slowed down. Remember, when you scale things up in quantum mechanics, energy spacings go down, which means like timescales become slower. So everything's happening like in slow motion, like in the real material. Now, of course, this is easier than said, you know, trying to scale everything up by a factor of 10,000. How do you actually do that? I mean, how in practice can we do that? And the way we do that is actually create these lattices artificially by interfering laser beams, like this arrangement, where you have 2 counter-propagating beams. They give rise to an optical standing wave with intensity maxima and minima, which is just half the wavelength in this configuration of the laser beams. And then by doing this in very different directions, you can basically synthesize any kind of lattice structure you want. Here's actually a nice picture from Ted Hensch's labs, where he basically did a very simple experiment. He took basically a big laser beam, he took a laser beam, sent it through a beam expander, and then through an aperture. This is really a macroscopic aperture. It's not like a small hole, like with 2 holes in it, and then focus the beam down again. Okay, and for 2 openings, what you get actually is what you all know. You get the nice double-slit interference pattern out of these atoms, okay, for these light fields. Now, if you do that with 3 holes, like this, you actually see you get this nice triangular hexagonal pattern again. And if you do this with something even more complex, like this 5 holes, you get this nice quasi-crystal structure. So you see, actually, by optical interference, you can create these beautiful, first of all, patterns of light. But for us, they are more. They are really, these intensity patterns that we see here, they are experienced by the atoms as potential structures. So this is a light potential that we can turn on these atoms, and they can be trapped and stored in these light potentials, and we can study their motion in them. Now, of course, these light potentials are not very strong, and that's why we have to go to very low temperatures to actually trap atoms in there, to load cold gases of atoms inside these light fields, and then they will be held in free space by these crystals of light. And we can study their behavior with each other. Now, typically, the systems we're going to look at are a few hundred to 1,000 particles when we talk about really resolving single atoms in these systems. And the systems we can actually look at are, on the one hand, spin systems. So we talk about qubits again. We're in the language of qubits. We have spin ups and downs. Yeah, sorry, I don't know what the synchronization. I tried the other adapter, but this one's never. That doesn't work at all. So maybe we'll have more success later. Okay. So, but I think the great advantage, the really big advantage, is that you can directly simulate these particle systems of bosons and fermions, which are of course important in the condensed matter context, material science context, because we're talking about electrons in a lattice moving, interacting, not just qubit systems. And actually, if you want to study such systems in material science, if you want to use a quantum computer, for example, to study such systems, you will have to map these problems of interacting fermions onto a qubit system. And this mapping is actually very complicated in terms of mapping the particle problem onto a spin problem. Can generate very non-local interactions. I don't know if we'll talk about the Jordan-Wigner transformation. Somebody of the theorists will mention that. But that's how you could map that. And that gives rise to very non-local interactions, which are actually very hard to realize and which have actually a lot of overhead in terms of size of the system. So we don't have that here. And that's a big advantage that we can study that directly in these systems. So let me summarize again why we can study, the physics of real materials in these dilute gases, which are 5 orders of magnitude more dilute even than the air surrounding us. That seems a bit surprising, but remember in quantum mechanics, in quantum many-body system, the only thing that matters is whether you are in a collective quantum degenerate regime or not to study collective quantum behavior. And the only thing for that to happen that matters is the ratio of the de Broglie wavelength over the inner particle spacing. So if we said now that the inner particle spacing is 10,000 times bigger than in a real crystal, going from angstrom to micrometer, that means, of course, also for us, the challenge as experimentalists is to make this lambda also a factor of 10,000 times bigger than what we have typically. Now, making lambda big, remember how lambda goes here is like 1 over the square root of the temperature. So actually lambda, to make lambda big, means we have to go to these ultra-cold temperatures. And that's why we have to kind of pay a certain price. And this price is, of course, to work at these nanokelvin temperatures, microkelvin temperatures to reach this ratio. But then, if you have that, then actually you have the same lambda already, and you can study the same collective quantum effects in both of these systems. Okay, so for those of you who are theorists who have never stepped into one of these AMO labs, this is how it typically looks. This is actually one of our most complex setups. A lot of lasers that do the cooling, the imaging, the lattice light fields we talked about. This is actually not even the actual experiment. This is just the optics table where we prepare all the optics. We send the light laser beams that we send to these optical fibers to the other table. And typically the pupils, they think this is the storage room for the optics when they come to visit us. But the fact is, the ones who know that if you turn a signal on one of those mirrors, the whole experiment does not work anymore. Okay, so that's why it's kind of still challenging, but we're small teams of 4 to 5 people working in the lab on these experiments. Another point to mention, which will come up, I think, also a lot in the lectures, is we're really talking about almost perfectly isolated quantum systems. Okay? And so it's very different than hooking up a material to a cryostat where you have a big thermal reservoir which does the cooling and cools down your block of material to a certain temperature where you study your low temperature physics. This is not an isolated quantum system. What we talk about here are systems which are almost isolated from the environment. They're not connected to any reservoirs. We're in fact talking in this vacuum vessel here, this glass cell, which is evacuated to have a very good thermal, sustain a very good thermal gradient. If you think of this cold gas cloud that I talked about, this sits behind this window here, 2 millimeters behind this window, and it has just a few nanokelvin temperatures. And everything else in this apparatus is at room temperature. So there's nothing cryogenic going on here. That's kind of a little bit remarkable. One thing you might wonder about, what about black body radiation? This is something to maybe think about. We can talk about it at the end. Doesn't the system thermalize with black body radiation? Why is that not a problem? We're not shielding against black body radiation, so somehow the system should thermalize. Yes?
Also, this these potentials are created by some lasers that are kind of driving the system as well. Maybe at some very highly tuned frequencies.
Yes, so we tried, for now, the only thing that I want you to think of these potentials as conservative potentials.
Okay.
So they do not do any cooling, they don't do any dissipation, they're very highly tuned, as you say, so the laser is very off-resonant with a specific transition in those atoms, but still not so off-resonant that it creates no effect, but it creates this feeble effect of creating this potential. And any dissipative effects we want to neglect for now. That's a whole topic by itself, but we want to just view them as conservative potentials in the course of most of the spectrum. All right. Any other questions? Okay. All right, so this is the system we're looking at. This is how it looks in practice. And let me show you a few things that you can measure in these systems. Let's, for example, now load atoms into this crystal of light. And let's try to see what we can detect with them. And the first thing that you could, for example, detect is measure, for example, momentum distributions. Now remember what we're talking about. We're talking about this, let's do 1D standing wave. So we have this periodic potential, right? So this is the potential. We can think of this potential as locally as pretty much like a harmonic oscillator. Okay? So if you would Taylor expand each lattice side, you could do that, and you in your first expansion, quadratic expansion term, you get a harmonic oscillator, so you have these harmonic oscillator levels. Of course, now you see these are tunnel coupled, so there's wave function overlap, so that's why the particles can tunnel from one side to the next. We never discussed the fact that they go over the hill. This would be classical motion, so for us they really move quantum-mechanically through this, meaning that they go through this tunnel, for example, from this side with this ground state wave function of my harmonic oscillator to the neighboring side. Most of the physics we talk about will be actually confined to this lowest band. And now we can ask what are the eigenstates of the particles in this lowest band. Okay? This is a problem you've probably solved in your quantum mechanics course. These are, of course, the celebrated Bloch waves. Now I'm thinking of them in this kind of localized wave function picture that we have here. We can actually think of them very simply and just let's try to make a very simple case of just two wells, where we would have, basically now confining ourselves to the ground state, we would have two eigenstates being the ground states of this double well. Okay? So simple abstraction going from the multiple well case to the two well case. What are the eigenstates of this double well case? You think of them? Yeah? Correct, the symmetric and the antisymmetric state. So you have these Gaussian ground state wave functions, and then we have the symmetric and antisymmetric linear combinations, which form the eigenstates for the double well. Which one's the ground state? The symmetric or the antisymmetric one? No interactions. So far, no interactions. Just single particle physics.
It means the sign of the tunneling.
Oh, the sign of the tunneling. Okay, let's J. Let's say so. We have minus. Okay, that's true. So I want it like this with J being positive. Okay. So this would be my second quantization language. How I describe the tunneling with J. I want J to be larger than 0.
Symmetric is lower.
Symmetric is lower. That's correct. So the symmetric is the ground state. So if we think of this as these eigenstates, we have the symmetric state here and the antisymmetric state, and we have psi left plus psi right here, 1 over square root 2, and the excited state would be 1 over square root 2 psi left minus psi right. And now you can see actually we can generalize this concept to the multiple well case directly. So now my eigenfunctions in the multiple well case, they will in general, these Bloch waves for the lowest energy band will be superpositions of these Gaussian ground states. So here you remember we have coherent superposition of being the left and right side with different phase factors, with basically 1 and -1 phase factors. Here it's the situation is a little bit more complicated, but not much more complicated. We basically now sum over all those lattice sides, so we make a coherent superposition of the particle being on different lattice sides. And now we have this phase factor degree of freedom. Remember, we can put different phases here. Okay? And actually what now comes, what characterizes these different Bloch waves is the phase factor, which depends now on each lattice site. Okay, so you're superimposing these Gaussian ground state wave functions with phase factors that depend now on the lattice side. And in the case of the symmetric and antisymmetric state, this was in fact all of them being in phase, so this phase factor being 1. We'll actually discuss these other kind of states now for the multiple world case we'll talk about in a second. Okay. So now for the lattice case, it turns out that these phase factors, they basically change linearly from lattice side to lattice side. So there's kind of a delta phi phase factor which characterizes these eigenstates of the multiple well case. So each time you go from one lattice side to the next, you change this phase factor by a certain amount delta phi. When they're all in phase, we already discussed we have the ground state. You could already guess what's the excited state, what's the most excited state that you can create for such a configuration. What superposition state would that be? In analogy again to this stuff. Yeah, sorry, so, yeah, oh yeah.
Spin waves.
Yeah, exactly. So this would be, of course, the wave where we superimpose like positive, negative, positive, negative, positive, negative. That would be a pi phase shift. Remember, pi e to the I pi is -1. And each time I add e to the I pi, this generates exactly this plus minus structure. Okay, so we have this would be the case when I have a phase shift of pi. Then we have the ground state would be the phase shift of 0. But now you can imagine what all the other states will be. They will be just different phase shifts between 0 and pi that you can have, that you can put here. Okay, this phase shift. And those are the Bloch waves. Okay? Maybe you derive them differently in the context of your quantum mechanics course, your solid state physics course, but this is how we can think of them here as this quasi-momentum, this Q, that characterizes these quantum states, tells us what eigenstate are we actually talking about. This quasi-momentum is basically just the phase shift that we have, this delta phi, between lattice sides, or Q times A, Q times the lattice constant, just characterizes this phase shift that we can have between the different lattices. Okay, and now you can understand how this band structure emerges, and we know the eigenstates, we'll come to them in a second. So now imagine we start with a free particle. In the free particle, we have just a p squared over 2m dispersion relation for non-relativistic particles. Okay, so this is what I've plotted here. A little bit strange because I'm already plotting it in the so-called first Brière zone, because this is going to be important now when we turn on the lattice very weakly, because the moment we turn on the lattice very weakly, we're going to get Bragg reflection of our matter wave particles moving from the lattice whenever their de Broglie wavelength matches kind of the lattice period. Okay, so if a particle wants to move in the lattice, when it matches the Bragg reflection condition, it will be reflected, it cannot propagate, and that's why you see what happens when we turn on the lattice very weakly. You open up these weak gaps in the energy spectrum. Okay, and these gaps happen precisely at these quasi-momenta that I quoted here. But you see, I've just done nothing different than just taking the p squared over 2m, folded it into this Brière zone, and gaps open up when I basically turn on the lattice stronger and stronger. But you also see that these energy bands that we get, remember, the states we talked about were these states in the lowest energy band. Okay, everything. So this was the ground state, and the pi state, where you had this e to the I pi flips, this was here at the band edge. And the other states are in between, where you have these different quasi-momenta changes, phase shift changes. What you also see, but that makes sense, that these energy bands get flatter and flatter the deeper the lattice gets. Why does that happen? Well, if the lattice gets flatter and deeper, this tunnel coupling will become smaller and smaller, will go down exponentially in lattice depth. Okay? And the weaker this tunnel coupling is, the less important the phase factors go to the limit of where you have decoupled harmonic oscillators. For decoupled harmonic oscillators, it shouldn't matter at all for the energy what phase factors you put in front of those localized terms. Okay? And that's what you see here. This is what the numerics also gives you. I've put a few slides in the back of the talk on how you can calculate this. I don't want to go through the discussion. I really would like to focus more on the intuition, how these energy bands and the corresponding states arise, but the formal derivation I've put in the slides, and you can have a look how you can actually calculate that. All right, so we understood that. Here are the wave functions that we already talked about, so we know them also. Yes? Yes?
Why isn't there a band gap between like the grade one and
smaller and smaller. This band gap gets basically exponential, gets much smaller in the system, but there is also a gap there. You just don't see it on the scale. So you're talking about here and here. Yeah, there is one there too. It's just really much smaller. Okay, so let's go back to the ground state. We're just discussing the slowest energy balance momentum h by k, which gives this pi phase shift between lattice sides. When you multiply this h by k of your lattice light with the lattice constant a, you precisely get this pi phase shift. And if I plot the density of the two, you can see they look actually quite similar, the probability density. But like in the symmetric and antisymmetric wave function, because of the zero crossing, the antisymmetric wave function really has 0 points here, 0 probability points, and therefore has therefore basically is this excited state that you create in the system. All right, good. So how can we measure that? Well, one way to measure those is to actually just look at the so-called time of flight of such matter waves that we can create in the lattice. Let's say you realize one of those matter waves, one of those Bloch waves in the lattice, in the lowest band, and you want to detect it. And one way you can do it, you can basically rapidly turn off the lattice. And we can do that because it's just laser light, right? I just shut off my laser and the lattice is gone. I can do it very quickly. So now what will happen is that these matter waves that I loaded into this optical lattice will expand. And they will interfere. So in a sense, what we're doing here is just a reverse experiment of diffracting a laser beam from a material grating. Okay? Here we're diffracting matter waves from an optical field. Okay? But the physics, of course, is the same. It's wave physics, and therefore what you then get when you measure the resulting far field intensity distribution is just a superposition of these basically emitted matter waves in the system that give rise to an interference pattern if we talk about coherent waves. Now this is how the interference pattern typically looks like, and now we can go back and ask what in this lattice determines what in this interference pattern. So what determines the envelope of this interference pattern of my original particles in the lattice, what determines the spacing here, what determines the width of those peaks. So let's start maybe with the width of those peaks, how narrow those peaks are. What determines that in your lattice, in your original lattice? Yeah.
To the number of sides.
The number of sides that you have, exactly. So the narrowness is how many slits you illuminate. How many matter waves you cover. How large is your system. Okay, very good. What's the spacing between the peaks? Somebody else? What determines the spacing between the peaks? Remember, what you're seeing in the far field is just the Fourier transform of what you have in real space at the position of the slits. Far field intensity distributions or matter wave distributions, they are just the Fourier transform of what you have in the real space. So everything that's, yes?
Your lattice constant?
Yeah, that's just the lattice constant. Now the last thing, what determines the envelope? Yes? The well depth, not quite the well, it could indirectly influence that, yes, but what feature, what tells me, what shape is this going to be? What determines what shape that function is going to be? You got 2 things right already, you just have to get the third one right and you're pretty good already. Don't worry, this is...
Is it just the shape of the potential, the main structure?
Yeah, indirectly, I want it more directly. What are these waves at the position of the lattice determines what this will be. And will it be a Gaussian, will it be a Laurentian, will it be a whatever, something. What determines what shape this function has? There's only one thing left. No interactions. You're already too complicated. It's all single particle physics. No interactions, just single particle physics. Yeah?
The shape of the single wave function?
Exactly. It's the shape of my ground state wave function. So if this is a Gaussian, like in our case, almost a Gaussian, then this is going to be a Gaussian. In optics, typically, of course, we have rectangular slits, right? When we diffract laser beams from material gratings. So what is it, if you have rectangular slits, what is this function here? That's a sinc function, exactly. Okay, precisely. And of course, you see actually again, what I told you, everything, the smallest scale here becomes the largest scale in the Fourier transform. It inverts the length scales. So the shortest scale is the wave packet size on a single lattice side. This becomes the largest scale in my Fourier transform, in my interference pattern. And of course, in the limit of delta function slits, this would just be a constant function. This Fourier transform of the delta function is a constant. Right? And this is indeed how the interference pattern looks like. So we release our atoms prepared, for example, in the Q equals 0 ground state of the lattice by creating a Bose-Einstein condensate in this state. So all bosons are in the Q equals 0 quasi-momentum state. We know now what this state looks like. We release it from the lattice, from a two-dimensional lattice, and indeed you see this beautiful interference pattern emerge. Okay, so this is the matter wave interference pattern. And from this matter wave interference pattern, I can tell you precisely which Bloch waves the particles were in. That gives a very distinct pattern. Because if you go to a different Bloch wave, for example to the pi one with pi phase shift, you see that the interference pattern has a vanishing central maximum, because there now you have destructive interference where before you had constructive interference of the waves, and you get these other peaks emerging here. Or if you have pi by 2 quasi-momentum, then you get this skewed interference pattern like you can see here. So from each of those matter wave interference patterns, I can basically read off which Bloch state I am populating in my lattice. All right, everybody happy with that? Okay. So the next thing we want to discuss when we talk about particles moving in this lattice or wave packets moving in a periodic potential, we have to look at the dispersion relation, which tells us that. And one way to talk about a wave packet centered around a certain quasi-momentum moving in the lattice is to take how fast does this wave packet move in the lattice. Actually, we have to calculate the group velocity. And the group velocity is nothing than the derivative of the dispersion relation with respect to Q. Now, I didn't derive that. Again, it's in the slides I have in the back of my talk for you. The dispersion relation for the lowest energy band in this lattice that we saw has this form minus 2j cosine QA. Q was this quasi-momentum, remember, this phase shift term, QA. J, that was the tunnel coupling, told you how strong these walls are actually coupled to each other. That depended on the lattice depth exponentially. And then the dispersion has this very simple form in this band. This was the Q equals 0 state, the ground state. This is the Q equals pi state, the highest excited state, and everything in between. Now if I take the derivative of that with respect to Q, I get velocity, the group velocity, and you see that's actually maximum at these points when I have pi over 2 quasi-momentum. So if I create a wave packet around pi over 2 quasi-momentum, that will move fastest in the lattice. And interestingly, the higher the quasi-momentum is, actually the particle can stop again. So it's not at all like in free space, where you would have higher quasi-momentum, higher momentum gives you higher group velocity. In the lattice, actually, at this point, you even have a particle, a wave packet that completely stops. So the group velocity strongly depends on the quasi-momentum and its maximum at this point of pi over 2 quasi-momentum. All right, we're going to make use of that actually also. So the fastest velocity, actually, we can calculate that. If I take the derivative with respect to Q, that will give me just 2JA, and then we'll have to divide by h bar. So the velocity is actually 2JA divided by h bar. That's the fastest velocity a wave packet can move in this lattice, in this ground state lattice. It cannot move faster. Okay, we'll come back to that because we'll check that in the experiment. All right, one final thing we need to talk about is this interesting phenomenon of Bloch oscillations, which basically allows us to change the quasi-momentum by applying a force to the particles, and applying a force to the particles in the lattice means just applying a potential gradient. Okay? So if I would, for example, now apply a potential gradient giving rise to a force, then we can easily understand what's going to happen with our different wave packets, because each of them sits now at a different energy in space. Its energy is going to evolve with its eigenenergy Ej at that specific point times T over h bar. And if they're sitting at different energies, that means there will be a phase gradient, phase difference between those two wave packets appearing as a function of time, which depends on the gradient times my lattice spacing times T. Which means actually now by a gradient, I can change the quasi-momentum. I can move from Q equals 0 to any point in the quasi-momentum that I want to reach. Okay, and that just expresses that we apply a force for a certain amount of time, that will change the momentum of our system, but here we have an intuitive way how this works in the lattice. Okay, by just imprinting these different phase factors on the lattice. And here's a case where we did that. You have delta phi equals 0, you see the symmetric interference pattern, and for delta phi equals pi, you see after applying the gradient for a certain time onto this state, you evolve into this delta phi equals pi state. All right, yeah, I think we'll skip this part. Let me now go to the interactions and add interactions to this. Again, we're sticking with bosons for the moment. And now we're just adding this very simple interaction part. So again, we have this part of the atoms tunneling on the lattice in the lowest energy band. And now we're adding this interaction part, where this interaction is a simple so-called two-particle, two-body on-site interaction. So you see when we have two particles on the lattice side I, this operator counts the number of particles. So this would give me 2. For example, if I have 2 particles, 2 times 1 divided by 2 would give me an interaction energy of U. Okay? For 3 particles, it would give me 3 times 2 is 6 divided by 2 is 3. 3U interaction energy. Yes?
In the previous slide, you had a comment about dephasing.
Yeah, I didn't want to go to the previous slide. But we can talk about it in after. It's a different way of measuring momentum distributions by a so-called technique called band mapping. But we can talk about it. I can explain that to you. It's basically, okay, since you asked about it, just explain what it's about. You know, to see these interference patterns, you have to suddenly turn off the lattice. You really abruptly, non-adiabatically have to turn off the lattice. But you could also ask what actually happens if you turn off the lattice slowly. What happens then? And then you can start thinking about it. If you want, we can talk about it over lunch or in the afternoon. Then you get a different way how that quasi-momentum shows up. And those are the two things that we have to contrast. But for now, I think we don't need that actually. So we can pass on the talk. Okay, so we want to add now this simple U interaction, on-site interaction. I guess John will also use that for his photons. No, you want to talk about that? Okay, so simple, same thing for the interacting photons. And we just, all the physics, all the atomic physics, we're hiding from you in this parameter U. Okay, so even if you don't delve deep into the atomic physics, how this arises through the scattering length and this on-site wave function, so the tighter we squeeze the particles together, the strongly they interact. That makes sense. But all the atomic physics we hide in this A and in this U parameter. And for us, actually, it's good enough to know that we have this U. This U for cold atoms can be pretty large, so it's a very large interaction strength that we can have. That is determined, can be actually positive or negative, depending on the scattering length. So it can have repulsive interactions or attractive interactions. Or sometimes we can even tune to non-interacting cases where we have no interactions at all. But that's good, always a good reference point. So we can always contrast the non-interacting case to the interacting case. Okay, so this simple Bose-Hubbard model that we talk about, only one parameter that matters in determining the phase diagram of this is the ratio of interaction energy, this U, to kinetic energy, which is this J. Okay, how large the tunnel couple is. That determines what phase you are. And if you are in a regime where this is large, then actually you're in the regime of strong interactions. And if you're in a regime where this is small, then you're basically in the non-interacting or weakly interacting regime. So let's go through the different ground states that we have in those two cases. So for the weakly interacting regime, so gamma small, you remember we could put all the bosons in the Q equals 0 state. That would be the ground state of the system. So remember, we had I'm asking the following. So we have this kind of dispersion relation here. So this is quasi-momentum versus energy. We're just looking at the lowest band. So this is my dispersion relation minus 2J cosine QA. We're talking about bosons and we're talking about the ground state. If they're not interacting, the lowest energy state means putting all of them in this state. Okay, that's pretty simple. All of them in this state means also that they are described by one macroscopic wave function, because all of them are the same wave function. We can describe the system by one macroscopic wave function. And if we do a diffraction experiment, we saw we got this nice diffraction result. Okay. Now, one thing we can also look at is actually what is the particle number distribution of the particles on my lattice. And what you actually find that's actually a very disordered distribution in this case. In fact, for large number of lattice sites and large number of particles, you can approximate the on-site particle number by basically a coherent state. I just write it down for reference for you again. You remember maybe from your Quantenoptics course, alpha to n, square root n, factorial n. So this is the state, how I can think how particles occupy a lattice site. Okay. Coherent state means it's the best approximation we have for a quantum mechanical state to a classical state. So this is basically gives rise to a, we calculate, for example, the expectation value of the field operator on lattice site I. This will just give us alpha. And so this is basically our classical field psi that I can think of having on this lattice site I. Okay? So this you should always think of as the best classical approximation, best quantum mechanical approximation to a classical field state. If you calculate the particle number distribution, well then you just have to project onto n and then onto a specific particle number and square that, then you get Poissonian particle number distribution. You also remember that. And that actually means that the particle number distribution on each lattice site is quite random. So if we could make a photo of this system, and we'll come to that actually soon, then you would see random distributions of particles on that lattice. Okay? So it's a state which is highly ordered in its coherence properties, has these nice wave properties, but if you look at it here in the lattice, it looks like completely disordered. The only thing you can tell is the probability for 0, 1, 2, or 3 particles to occur. This would just follow a Poissonian distribution corresponding to these coherence. Now you can immediately tell that for strong interactions, this cannot be a good ground state of the system. For very strong repulsive interactions, for a very large U, such a state of 2 and 3 particles on a site, that will cost you a huge amount of energy if the interaction energy is large. If U is much larger than J, it cannot be good to stay in this state. So particles reorganize, and the new ground state for strong interactions would be a state where you have exactly 1 atom per lattice. Because like this, you could avoid having any interaction energy cost if you just have 1 particle per site. Obviously, this is something completely different than this, because this is not described by a coherent state, but now we have talking about Fock states with a precisely defined pattern number distribution per lattice. Okay. All right, and of course, if you do an interference experiment with this state, what you actually see is a vanishing of the interference pattern. The only thing that's remained is this shape. What determines again the shape of this cloud? Why is the cloud now? What this interference pattern look like this? What determined that shape?
Potential.
Sorry?
The potential.
Yeah, we had it before. Not shape of the Fock states, just tell me occupations. What do you mean by shape of the Fock state? The shape of this Gaussian ground state wave function on the lattice side. That's the only thing that remains, right? So we now, what happens, you can think of these waves as being emitted from each lattice side, but because we're dealing with Fock states, the quantum uncertainty of the phase of those matter waves is large. It's between 0 and 2 pi. So you can think of this pattern that comes out here as emerging as a result of, let's go back. Here, many emitters, but they're basically now emitted with random phases. Okay? And if you have many emitters and emit them with random phases, the interference pattern will vanish. Okay? You can check for yourself on a computer. If you have a large number of lattice sites, then you will see that this actually vanishes very nicely, and this is what happens actually here in this configuration, that you basically end up with a state that has no coherence, but order in particle space, but here we have a state which has coherence, but no order in particle space. So you see they are like two dual-sided metals, two dual sides of our metal, the strongly interacting state and the non-interacting state, and we can think of them as kind of this uncertainty relation between phase and particle number variance, which for macroscopic quantum field is explaining us why that happens. So if our fluctuations in the particle number distribution are large, then the fluctuations in the phase of the coherent field will be small, which will be the limit of coherent states. On the other hand, if my particle number fluctuations are 0, then I will have maximum phase fluctuations, and I will have these large quantum fluctuations in the phase described these random interference, actually emitters that I showed you before. All right. Good. Any questions so far? Are we getting along? Too slow? Too fast? Are we doing with the speed? You just tell me. you know everything already? Or? Yes.
The argument so in this ground state, like for strong interactions,
Yes.
so we know the number very well, and then like the phase becomes random, and then they interfere, and when you average them out, they kind of washed out, right? That was the argument.
Yes.
Okay.
Precisely. If you think of it's trying to expand a Fock state in coherent states. What you find is actually, in order to realize that, you need to have superposition of all coherent states with all possible phases.
Oh, I see.
Okay. So in a single snapshot, I can think of this as being emitted as a wave with a random phase.
Okay.
In a single snapshot. Precisely. Very good. Okay, good. All right, yes, and that's of course what I missed the most important thing. The most fun part is actually what lies between those two regimes. That's actually what people call a quantum phase transition, where even at t equals 0, you have this transition between this state and that state here. And I don't know, Thierry, are you going to talk a little bit more about quantum phase transitions, about this?
We already talked about
Okay. Okay, just point you to the fact that the real interesting stuff, actually most interesting stuff, happens at actually how the system changes over from this one state to the other state.
We were supposed to also be delivered.
Yes, I know. Yeah, well, we're coming to it.
But if there is a demand, I'll be happy.
Okay. Actually, we will see that a lot of the out of equilibrium dynamics we talked about on Thursday then is actually interestingly connected to the ground state physics. So it's not, so there's a connection between the two. Okay, so finally I just want to complete the picture for fermions because we started with fermions. For fermions, the phase diagram looks slightly different, but you also have similar things. So you have now a mixture of up and down fermions in the lattice, you cool them down, and the first thing that you encounter for repulsive interactions is basically if you cool below this interaction, repulsive interaction energy scale U, you will also get this state with one fermion per lattice side. Just as for the bosons, you get what we call one insulator. Now for these fermions, mixture of spin up and down fermions. And one thing we'll talk about tomorrow, then actually if you cool below another energy scale, which sets an energy scale of spin-spin interactions, the so-called super exchange energy scale, these will actually order antiferromagnetically into a Heisenberg antiferromagnetic. And we'll talk about why that happens in the dynamics of such systems tomorrow. All right, so the last part, how much time do I have left? 7 minutes. 10 minutes?
At least 10 minutes.
Yeah, then let's talk about these new ways of detecting these things, because then we'll connect, of course, also to a lot of the dynamics experiments we'll talk about and tomorrow on these quantum gas microscopes. So imagine you have, for example, this ground state wave, this many-body wave function, psi of your many-body state, bosons or fermions in your lattice. And in general, we could write this as a coherent superposition of these different occupations, configurations of particles in the lattice, right? I think in the most general way. Of course, there would be complex phase factors in front of these coefficients as well, which is expect for now. And let's imagine we would now have a camera that could take single site resolved images with single atom sensitivity of such a state. What would happen? Well, if you take a photo, then this state will collapse. It would collapse randomly onto one of those configurations. Okay? So this would be the state that you see in that photo. Of course, quantum mechanics does not predict us which of the photos we're going to see. It's going to be completely random. We just know with a certain probability, depending on these prefactors, of course, norm squared, we will see, for example, this or that configuration. So if you prepare psi again and measure, you collapse onto a different state. But by repeating that many, many times, you can basically now get access to the probability distribution of the different configurations. Okay? I can tell you how often does this configuration occur, this one, that one. And now from that, I can actually answer a lot of intriguing questions. I can answer how does, for example, the presence of these two particles is correlated with having another one over here and a hole in between. Okay? And these are already non-local correlation functions that go beyond anything that you would measure in a standard condensed matter experiment where you are actually basically, well, correct me, my colleagues, we are always confined to two-point correlation functions. Okay. So this is interesting because now we have access to multi-point correlation functions here in the particle configuration space. And we know how to do that also for currents. So in principle, we can extend this analysis to currents. So I can define a current operator in correspondence to the particle occupation operator, and I can measure current distribution on different bonds. Okay? And then I can correlate also currents on different bonds. So I can measure current correlators also on higher orders in these systems. All right, how does this work? In these microscopes, here's kind of the schematic, how this is done. Remember, we have these micrometer spaced lattices, so we can just use a good microscope to look into them. So what we do is we first prepare a single plane, single two-dimensional plane of the system. We use a single plane because the depth of focus, when you go to the ultimate resolution of this objective, ultimate resolution would be lambda over 2, of course, which you can reach with this objective. If you have lambda over 2 resolution, then the depth of focus is also lambda, basically. So the depth of focus of this objective will be very shallow at this point, so we confine ourselves to a single 2D plane, which is then in focus for our objective. And then we create these lattices, for example, in the XY direction, or triangular, hexagonal lattices, whatever you want. And then we suddenly turn on near-resonant light that scatters off these atoms, so they fluoresce. And this fluorescence is captured by this objective and registered then on a CCD camera. And the fluorescence is then basically the moment where you start scattering the photons is precisely the moment where the wave function collapses from this psi onto one configuration. And okay, once it collapsed and you see a certain particle configuration, the system is destroyed, it's measured. We don't have psi anymore, we have the collapsed wave function on one particle configuration like you can see here. But you see also that you really nicely see each individual atom here. This is a boring thermal state, we'll get to more interesting ones in a second. Alright, this just shows how this is done. Well, one slight thing that I have to mention that concerns almost all experiments, apart from the fermion experiment I'll talk about on Thursday, is that there's an unfortunate AMO effect called these light-induced collisions that's happening in these systems that for most experiments confine us to measuring actually the parity of the occupation, not the actual occupation. So what is this effect? So basically, in just a cartoon picture, it means whenever you have two particles on the lattice side and you turn on near-resonant light, there's so much energy released due to this unwanted light-induced collision process that the two particles are ejected from the trap. Remember, the light potentials are very weak anyway. They're very shallow, they're not very deep. And they're like basically when you turn on light and have two atoms confined, it's like a small bomb going off and the two particles are expelled.
Is this the imaging light that causes light?
Yeah, this is the imaging light. Of course, it's not the lattice. It would be horrible if it would be the lattice light and we couldn't do any physics, okay? That would be, the physics lattice is conservative, does not have this effect.
It's classical, almost classical.
Almost classical, yes, for us. We don't even have a cavity or something around it, but John will tell you that things get even more interesting if you can have back action of the atoms to the light. We don't have that. For us, the light just creates a classical field, classical potential, conservative potential. This is detection. Same detection.
Yeah, so but the time scales are also important here, right? If the time scales of these collisions occur more slowly than the time scales of the photons scatterings, then you can actually...
Okay, so how do we image faithfully? Okay, so to image faithfully the state, we do the following. You work in a shallow lattice where the particles generate the many-body phase we talked about, maybe this rod phase, maybe this thing. And then to image, first of all, we make the lattice extremely deep, suddenly, so we quench the hopping. So particles at that point cannot move anymore. But the configuration is still frozen in. So we do that non-adiabatically, so the particle configuration is just frozen in from that state psi that we created here. Okay? And then we scatter photons. Okay? And that photon scattering can now, should not change the occupation anymore. So we have to be careful that this photon scattering does not heat the particles to roll over the hill. Okay, if we go then, classically are heated to move from here to here, and then suddenly we see two particles here and zero here. That's not from the original state, that's just an artifact of our imaging. Okay, we don't want that. So we have to take great care in providing cooling and fluorescence light scattering to make a faithful image of the particle configuration of the lattice. And that's what we do. So trust me that we have that under control. But you're completely right. But of course, again, after you measured it, it's collapsed. And then we can take images, images like these fluorescence images here and send them through an image analysis program which basically knows that there is a lattice, so there are only discrete sites where particles can sit in the system. In the parity projected version, we can either only detect 0 or 1 particle, because everything is parity projected, remember, due to this artifact, this effect. And from that, we can actually then use this computer program to, knowing the point spread function of our imaging system, to reconstruct the occupation of the lattice with particles. Okay. And then I give my favorite theorist, I just give this image. Okay. This is just a 0 and 1 matrix of 0 and 1s determining where the particles sit. And we make hundreds and thousands of these images, which are these configurations, then we can determine these correlations, these interesting correlations. Okay, so this is all our part, how we get here, and from then we can pass it on to people who analyze that. Yes?
How long does it take to do each shot?
Yeah, so that's a good question. So right now for this experiment, it's about the whole cooling cycle, preparation cycle is about 20 seconds. Then the imaging takes about 1 second to get enough photons. To scatter enough photons that we see them on our camera. So that's basically the cycle. And then we have to recreate psi, or the density matrix, or general framework, measure again, collapse it, destroy it. And about this destruction, we can't do anything about it. It's a fundamental quantum mechanical process. Once we make a strong measurement on the system, on the particle occupation base, it has to collapse. All right. Yes? The spacing is, again, in this case, it's a half a micrometer. We'll see lattice sites up to 200, 300 lattice sites. Okay. This will vary a little bit in the talk, depending on the system. Okay, so that's finally at the end of the talk. Let's put everything together we learned, the theory and the experiment, and look at this. You know, remember we had Mott and superfluid had these really dramatically different ways of how they should show up in the particle picture if we image. And this is what you see here. So here's a Bose-Einstein condensate image with this fluorescence imaging technique. Here's the raw fluorescence image, here's the reconstructed one, and here's our image analysis of where the particles are. And you see that it really has this dramatically fluctuating particle number occupation. Remember, in principle, if we would have 0, 1, and 2, and 3 resolution, we should see this Poisson distribution. But since we only see 0 or 1s, we see always just a parity projected one. But the large fluctuations show up, and you see this looks like a Swiss cheese. Basically, in terms of homogeneity of where the particles are. Okay. Now again, what you see here again is a single shot. If we would measure again, it would look totally different again. Now for strong interactions, if we make interactions strong, I didn't actually say how we make interactions strong again. So remember, we have these two parameters, U and J, and the ratio of U over J determined everything whether you're strongly interacting or weakly interacting. So there are two strategies of getting into gamma large compared to 1. Either you make U large by making this scattering length A large, that's by using so-called Feshbach resonances, or you can also make the denominator here small, then U over J will also be large. That's what we did initially, and the way easily how to do that is just to change your lattice depth, because J depends exponentially on the lattice depth. So the deeper the lattice is, the smaller J, exponentially smaller J becomes, and you basically can reach the strong interaction regime. And that's the only thing we did here, and then we made a photo. And now look how different this looks. So this is basically now a Mott insulator, almost perfect occupation, you know. In the system, we can actually fill it up with more and more particles, and you see this strange hole appear here. What's the hole is actually here, there's not a hole, there are actually precisely 2 atoms here. It's 2 atoms, but remember, due to the parity projection, we see them as 0 atoms. Okay, so this is what we call a wedding cake distribution, which gets larger and larger as we increase the particle number distribution. All right, so that's pretty nice, and you know, we didn't sort the particles; they really just sorted themselves by tuning to these different ground states in the system. Here's just a picture again of this. One thing I want to actually just stress at the end also, just to one more slide, is these fluctuations that we sometimes see. You know, that ideally at equals 0, there should be atoms here or an atom here, but you see they're missing. And the reason why they're missing is because we're not working precisely at 0 temperature. Because we're not precisely 0 entropy. There are finite thermal fluctuations, and these manifest as these particle hole fluctuations in the system. And actually, by just counting them, you can determine the temperature of the system. So that's actually how we can do thermometry, by just counting the number of these elementary defects that we have in the system, using elementary thermodynamics, in this case, in a grand canonical description. And for example, take an image like this one and determine precisely temperature, chemical potential, and particle number in the system. Okay, so this was like 600 particles, chemical potential 1.17 U, and 0.07 U temperature, which was probably in this case just a few nanokelvin temperature that we can determine from that. Okay. So just by counting this number of differences. All right, yeah, then let me stop here, and I'll talk tomorrow how we can do this for fermions, how we can get spin resolution for fermions. That's important because we really not only want to know where the spin ups and downs are sitting, and get more information how we can apply that to the system. All right, I'll do that. Thank you for the first lecture. Thank you very much.
Additional questions?
How do you resolve spin states?
Wait until Thursday. I'll tell you. Okay. Basically, we make use of a Stern-Gerlach.
Oh, I see. Turn on magnetic fields.
Yeah. So I'll show you. But we can only apply it at detection. So we don't want Stern-Gerlach fields to be present during the experiment, where we create a certain phase we want to analyze, because that would be a different totally. So I'll show you how to do that. How we get full spin and density resolution. In the language of condensed matter physics, is full spin and charge resolution.
Is there any advantage gained from directly controlling U instead of J?
Yeah, there is. I would, if I have the chance, I would always try U, because then I can keep the time scales for particle rearrangement. They will always be J. Remember, the particles have to reconfigure, and the time scale for them to reconfigure will be set how fast they can move through the lattice. And if you quench J, that also means that time scale will be very slow, and you will be susceptible to vibrations, fluctuations, much more susceptible. So if you can keep all the energy scales involved as large as possible, you're in a much more favorable situation. So why don't we always just make U very large? Well, if you make U too large, there's also some AMO physics that hurts us. Then you run into the problem sometimes of so-called three-body recombination. The loss process, when three particles come together, there's a very strong loss actually. And we don't want that either. So that usually you have to find a compromise between making U as large as you can to have a large J to be in a strongly interacting regime. You always want gamma, the interesting physics we want to study is mostly for gamma large compared to 1. We want to look at strong interaction.
And then the other advantage is that the temperature is less of a problem.
Yeah, as I mentioned, the fluctuations, the thing is just much more robust to any fluctuations to temperature. I wouldn't, because temperature, a priori, you see temperature, that's one thing, we're not connected to a thermal reservoir. So temperature changes all the time in our systems when we make adiabatic changes. Well, the only thing that remains is the entropy. So you should think of these experiments as being carried out at the best at ideal, at constant entropy. And whenever we change lattice depth and things like that, temperature always changes. And of course, Thierry is right in terms of when I have a heating source introduced into my system, I want to have these scales as large as possible to be as robust as I can against my heating source in the system. Now, maybe one final comment, this U is actually really large for atoms, and to make it large for photons, that was a real challenge, and John will tell you how to do that. So usually photons, when you talk about non-linear interaction in non-linear media, they're very weakly. You can never have this strongly interacting regime. You have to really do some very clever tricks to make photons extremely strongly interacting. For atoms, it almost comes for free. So,
but not today. I'm not telling you about that today.
Okay. Would you want to tell about it?
Yes, absolutely.
All right. Cool.
Yes.
So, additional questions? If not, let's take a short break.